Welcome back to Very Ordinary Differential Equations. In this lecture, we continue our study of non-homogeneous second-order linear equations with constant coefficients, addressing the case of a forcing function that is a product of polynomials, exponential, and trigonometric functions. So we're going to try to do a very general sort of problem. With our earlier knowledge in hand, we keep making more and more complicated forcing functions. For example, can we solve equations like 2y double prime minus y prime plus 5y equals x e to the x sine of 2x? We have a polynomial x, an exponential e to the x, and a trigonometric sine of 2x, all being multiplied together. Or what about this? Okay, so similar problems, polynomials times exponentials times trigonometric functions. Now what you could theoretically do, a polynomial like 3x squared minus 1, I could distribute this as 3x squared e to the 5x cos x minus 1 e to the 5x cos x. So if I had a general formula for a power of n times an exponential times a sine or a cosine, I could take any polynomial, break it apart, and apply such formulas over and over again. But that would be terrible. For each power n, you would have to figure out the relevant formula. It would be slightly different for sines versus cosines. And then anytime you had a polynomial, you would now have tons and tons of terms to worry about. So we're not going to do that, okay? We're not going to derive a huge complicated collection of formulas. Rather, we're just going to take all of our existing knowledge and the techniques we used to derive those formulas to attack these problems one at a time. So maybe we have ay double prime plus by prime plus cy equals f of x e to lambda x sine omega x, or the same thing with a cosine, where f of x is a polynomial. So a linear second-order equation with constant coefficients, and a forcing function that's a polynomial times an exponential times either a sine or a cosine. We're going to assume that f of x isn't constant. That's actually enough to guarantee that the forcing function is not a solution to the complementary equation. We know exactly what solutions to the complementary equation here look like. They're either exponentials, or x times an exponential, or an exponential times a trigonometric function, but they were never an x times an exponential times a trigonometric function. So for these second-degree constant coefficient equations, you can never solve the complementary equation with a polynomial that isn't constant times an exponential times a trig function. So we don't need to worry about what if our forcing function solves the complementary equation. As long as f of x isn't a constant, as long as it really does have powers of x in there, it's guaranteed not to. We're going to use something known as the method of undetermined coefficients. So finding a particular solution to an equation like this, or the same thing with cosines, where f of x is a non-constant polynomial of a given degree. If only the polynomial is present, you would assume yp is also a polynomial of that degree. Otherwise, if the polynomial weren't present, we would assume it was of the form e to the lambda x and then some combination of sines and cosines. We really just combine the two techniques. Assume yp is a product of a polynomial of degree n, along with the appropriate exponential and sines or cosines. Do be careful, every time you get a sinusoidal term, you need a different polynomial. So let's take this general approach and throw it at some problems. Find a solution to y double prime plus y prime minus y equals x e to the 3x, a polynomial x times an exponential e to the 3x. Now there are no trigonometric terms, which means we do technically need to verify that the forcing function doesn't solve the complementary equation. But r equals 3 is not a solution to r squared plus r minus 1 equals 0. So if e to the 3x is not a solution to the complementary equation, x e to the 3x certainly isn't. So with no trigonometric terms, we're just going to try a polynomial of degree 1, ax plus b, times e to the 3x. So even though this polynomial just has an x, I think that's a polynomial of degree 1, so my solution would be an arbitrary polynomial of degree 1. I might need a constant term in there. So I can compute the first and second derivatives. Here's the first derivative, there's the second derivative. Okay, it's just a matter of a bunch of product and chain rules. So we have a proposed solution, yp, and we've computed its first and second derivatives. We take those and we throw them into the differential equation. Yp double prime plus yp prime minus yp Well, after factoring the e to the 3x out of everything and collecting like terms, you will have 11ax plus 7a plus 11b. Comparing that to our desired solution of just x e to the 3x, we want 11a to be 1. We want the quantity of x's, 11a of them, to be equal to the quantity of x's, 1. But we also want our constant term, 7a plus 11b, to be 0 because we didn't want a constant term. So in our proposed solution, yp equals ax plus b times e to the 3x, we need two things to be true. 11a should be equal to 1, and 7a plus 11b should be 0. We quickly solve this as a equals 1/11 and b equals negative 7 over 121. Therefore, our solution is ax plus b times e to the 3x, or 1/11 x minus 7 over 121 times e to the 3x. Next, let's find a solution to 2y double prime minus y prime minus 3y equals x sine of 2x plus 3 cosine of 2x. Neither term is a solution to the complementary equation. Okay, the first one couldn't be. We never got complementary equations solved by x times a sine term. However, that second one of a cosine could theoretically be. However, the complementary polynomial 2r squared minus r minus 3 has two distinct real roots, which means a fundamental set of solutions is given by two different exponentials, nothing that looks like our forcing functions. Now, both sinusoidal functions have the same period and phase shift. We can actually attack them simultaneously. We're going to suppose that our proposed solution is a first-degree polynomial times the sine of 2x plus a first-degree polynomial times the cosine of 2x. The cosine term only had a 0-degree polynomial, but overall I have a first-degree polynomial times trigonometric functions of the same period and phase shift, so I really do want first-degree polynomials on both. Okay, we have used the same degree polynomial, but not the same polynomial. This is important. Okay, I did not use ax plus b in both cases. I did, however, use the same degree. So here's our proposed solution. We compute its first derivative. We compute its second derivative. We're rushing through these derivative computations, by the way, because it's sort of presumed that you can do this quickly on your own, and I'm just saving time in the video. But here's the first and second derivative of our proposed solution. I throw it into the differential equation, 2yp double prime minus yp prime minus 3yp. Well, we've got a whole lot of sines and cosines. This is how many sines I have, and this is how many cosines I have. And now all we have to do is compare this to how many sines and cosines we wanted. So this is what we got. Comparing to what we wanted, the quantity of sines that we have, I should have 1x of them, but no constant of them. Comparing the cosines, I want no x's of cosines, and the constant term should be 3. So how many x's of sines, how many constants of sines, how many x's of cosines, how many constants of cosines has given us 4 equations in the 4 unknowns a, b, c, and d. So whatever our proposed solution is, if I can make all 4 of these equations true, we'll be in good shape. Now the first and third equations, this one and this one respectively, because they only involve a and c, they can be combined against one another pretty quickly. And you'll solve that a is negative 11 over 125 and c is positive 2 over 125. Once you take those values and put them into the second and fourth equations, you'll get this. Okay, so this is what you get when you take the second and fourth equations up here and plug in a is negative 11 over 125 and c is positive 2 over 125. You'll get these two equations right there. So in our proposed solution, we've determined that a had better be negative 11 over 125, c had better be 2 over 125, and then we have 2 more equations to solve. Well, now these just have 2 variables in them, so I can solve this relatively quickly. b is going to be negative 197 over 3125, and d is 41 over 125. Therefore, I can go back to my y sub p and substitute for the now known values of capital A, capital B, capital C, capital D, and here you have it, a solution to the differential equation. As a third example, let's find a solution to y double prime plus 2y prime minus 5y equals 2x plus 1 e to the x cosine of x. Now our forcing function has a linear polynomial, an exponential, and a sinusoidal term, 2x plus 1 e to the x cos x. This means, by the way, it can't possibly solve the complementary equation for our second order differential equation. So we should assume that our particular solution yp has the same basic form. But since I have a cosine, my proposed solution needs to have a sine and or a cosine, and each one of them gets their own first degree polynomial terms. So we have first degree polynomial e to the x sine x and a presumably different first degree polynomial e to the x cos x. What we do with this is we compute its first and second derivatives and start solving for a, b, c, and d by comparing to the differential equation with the desired result. So we've got to compute its derivative. Okay, here's yp prime. Well, not all of it, there's the rest of it. Okay, so here's yp prime. Okay, it takes a lot of terms, but what we should do is group them together according to whether there's an e to the x sine x or an e to the x cos x. So here it is presented with all of this times e to the x sine x. Notice we'll have, for example, ax plus b. Here's an ax plus b. We'll also have a minus cx minus d, minus cx minus d. So similarly, find all of your e to the x cos x's, and it will simplify down as given. Okay, so here is yp prime. Here's yp double prime. This is just a lengthy application of various product and chain rules, which, once I collect all of the e to the x sine x versus e to the x cos x's, looks as follows. Okay, so now we have computed yp prime and yp double prime and grouped them according to e to the x sine x versus e to the x cos x. What we now need to do is take them back to this differential equation. Then we will again collect all of our e to the x sine x's and e to the x cos x's, and we'll compare to what we were hoping to get out. So here was our proposed solution yp, its first derivative and its second derivative. We throw all of this into the differential equation, okay, and there it is. Once I group together all of my e to the x sine x's. By the way, what I don't recommend doing is actually writing all of this and then all of this with a 2 in front of it, and then all of this with a minus 5 and expanding. Just know in advance you're going to have a bunch of things times e to the x sine x. They could come from yp double prime, in which case you'll get negative 2cx, 2a, minus 2c, minus 2d. There they are. You'll also get 2 of whatever you had for yp prime. There that is. And I will take away 5 of whatever I had from yp, minus 5 there. Similarly, what do I get for my e to the x cos x's? Whatever I had in yp double prime, there, plus 2 of whatever I had in yp prime, there, here's the 2, minus 5 of whatever we had in yp, there. Now you can simplify what's inside the parentheses without 37 different terms of e to the x sine or cos x possibly throwing you off. And that's what you'll get when you simplify everything down, okay? What is important is to keep track of what's multiplying x versus what's the constant term. So here was our proposed solution, ax plus b e to the x sine x plus cx plus d e to the x cos x. We took that, we threw it into the differential equation, yp double prime plus 2yp prime minus 5yp, and we have this expression here. Some quantity of x's and some constant, e to the x sine x, some quantity of x's and some constant, e to the x cos x. Now we just need to compare that to what we were hoping to get out. First of all, in our sine x term, I should have all zeros because we didn't want to get any sines. So how many x's times sine x? None of them. How many constants times sine x? None of them. How many x's times cos x? 2 of them. So 4a minus 3c should equal 2. And how many constants times e to the x cos x? Exactly 1 of them. And once again, we have 4 equations in 4 unknowns. So if our proposed solution has the form we wanted, then we've got these 4 equations and 4 unknowns to solve for a, b, c, and d. Now at this point, if you're using a computer algebra system or a calculator, it's totally fine to just go ahead and solve this using some matrix algebra. Okay, now, however, we can do it by hand. The first and third expression, again, only involve a and c, so I can play them off one another to pretty quickly give that a should be 8 over 25 and c should be negative 6 over 25. Once I have those values for a and c, I can take them into the second and fourth equation. Now there's no more a and c because I've substituted in those values, and I just have two equations and two unknowns here. So if our proposed solution is what we wanted, we've actually determined that a must be 8 over 25 and c must be negative 6 over 25. The other two variables, b and d, must satisfy these two equations here. But as two equations and two unknowns, we can solve them straight away. 264 over 625 and 77 over 625 is what you should get. Therefore, our solution must be ax plus b e to the x sine x plus cx plus d e to the x cos x, where a is 8/25, b is 264 over 625, c is negative 6 over 25, and d is 77 over 625. So here is a solution to our differential equation. Altogether, where are we? If you want to find a particular solution to a linear second-order differential equation with constant coefficients, where the forcing function is a non-constant polynomial combined with exponential and/or trig terms, suppose your particular solution has the same form, a polynomial e to the lambda x sine omega x, but don't forget a polynomial e to the lambda x cos omega x, where both g1 and g2 are polynomials of the same degree as the polynomial f of x that you were hoping to get out. Compute the first and second derivatives, then throw it into the differential equation. Group terms according to whether you have e to the lambda x sine omega x or e to the lambda x cos omega x, and then solve for your unknown coefficients. And be patient. These problems take quite a long time. Practice so that you know exactly what to do. The only question is actually carrying out the computations. This will generally involve practicing solving systems of linear equations and variables, okay? We had, in our examples earlier, two different problems where we had 4 equations and 4 unknowns. So practice solving things like that. You don't want that to be what slows you down.